For this video, I'm going to talk about work energy theorem. And what we need to recall from the last video is that work is an action that causes some sort of change to an object or a system. And energy is the cost or energy we can say it's the capacity to do that work. So what I want you to consider is a box. A box. There we go. Something like this. And let's say that we're trying to move this box. Maybe it's too heavy to pick up or whatever. So we're going to push it parallel to the ground for some distance. And let's say that distance is a straight line, or the path for the distance is a straight line, so it's our displacement. Second law says if we apply a net force, that box should accelerate. So across this distance, if the floor is smooth, the box should speed up. So what I want us to take a look at here is the relationship between the work and the kinetic energy. If we're applying a constant force, our acceleration should be uniform, which means that we can use some of our kinematics equations. So I want to start with a box at rest. And let's say by pushing it we speed it up to some speed v. Then we're probably using this equation here. And by second law we can say that our net force over our mass of the box, so whatever mass this is our acceleration. And we'll multiply by the displacement. Well, already it starts to look like we have a term for work. So we can make that substitution here. So the work we're doing on the box divided by the mass. And keep in mind this is the net force on the box. So this is the net work done by all the forces on the box. So there's still, if we draw a free body diagram, there's still gravity acting down on the box. There's still a normal force. And we are just pushing with F. So in this case, F is our net force, but even if there was some friction, if we knew the difference between these two, we could solve this for like speed or any other variable we needed. So back to this, we're looking at the network. Let's say I don't like fractions. So I'm going to multiply everything by the mass. And I want to get the network by itself, so I'll move this over here, this term, by subtracting it from both sides. Multiply, or divide both sides by 2. And we can see the relationship here. Network causes a change in the kinetic energy of an object. And that's work energy theorem. So if the frictional force was just as strong as the applied force, we would have no network, and the box wouldn't gain speed. So if it was already at rest, it would have just stayed at rest. If it was moving, it would have kept its own velocity. And that's work energy theorem. That the network that goes into the system should speed the system up by that amount. That's in an ideal world. Second law of thermodynamics tells us no process is perfect. So typically we have to put a little bit more work in to get the kinetic energy we want. But that's work energy theorem for you. So that's our missing kinematics equation, one that I didn't go over, and we'll see it again later. But I'll refer to it as the energy equation when we talk about kinematics from now on. And that's how the two are related. You as an external source, you are pushing on the box, so you are taking some of your energy to do work. So energy is coming in from your system and going into the box system here to give it kinetic energy. So we could even say that work or network is a transfer of energy from one system to another. Any work that's internal into the system, so maybe if this box was filled with like marbles or something, any collisions between the marbles are internal, so all that mechanical energy, or all that energy, should stay the same. Remember, I distinguish between mechanical and non-mechanical. Mechanical energy is simply all the kinetic energy in the system and all the potential energy in the system. So all energy in a closed system is conserved. It's just sometimes that energy will get lost in some form that's not easy to get back, and that's what we refer to as like non-mechanical. So in a perfect world, that transfer of energy should go smoothly, and we wouldn't lose anything. But what we need to talk about now is conservation of energy. When is it conserved? When is it not? What causes energy to go from mechanical to some form that we can't easily get back?